of elements. This is 2 elements. Yes, and the tetrahedral, the isometries of tetrahedral is another group of 24 elements, which is not, doesn't have any quaternion representations, and you can prove it, but it's really hard. You need to classify all representations. Okay, this is one. Another is about the last, which, yes, and people somehow fail to solve the, well, to indicate why you correctly produced a quaternion representation of a group, but you didn't forget to prove that it is irreducible. I mean, it doesn't make sense to speak of quaternion representation for non-irreducible things. So you have to prove that it is irreducible. So, okay, another was that you have the last two, that you have a rotation group, Z by N. It has a reducible representation in R2, so it's GL of R2. And you need to show that isomorphisms of that are automorphisms of that are 2-dimensional, if it is irreducible. Okay, this is rotation. And let's multiply everything by C2. Then this will be, this is abelian. And this was, you had such an exercise earlier that all representation of abelian groups are irreducible over C are one-dimensional. So this is C2, which is direct sum of 2 one-dimensional representations. So it's like C with this generator here acting as square root of n epsilon, and plus its complex adjoint, complex conjugate. So it's plus C with this action by square root of epsilon. Opposite this is just -1. Okay, then this is rotation. But every matrix which commutes with this, here you have like zeta, here you have zeta -1, zeta. This is the matrix of this. If you have another matrix which commutes with that, it is either diagonal or perpendicular. But it can't be perpendicular because there are 2 different values. Then it is also diagonal. Then you obtain that it is commutative, and also it's 2-dimensional because it's dimension 2 here. Okay, and then many people solved how you can deduce from that it is a number field, which is essentially nothing, because, okay, automorphism of these representations, there's division algebra, it's 2-dimensional, commutative. It has to be a number field, and then you check that all 2-dimensional number fields are actually quadratic. This was fine, except that you really had to solve this as well. Any more questions about the exercise assignment, the tests? Yes?
You use the diagonals, the matrix between C, right?
Yeah. So I take R2, multiply tensor by C, obtain C2.
So it has dimension 2 in C, it's in the same as
But it stops being irreducible. It's no longer irreducible. It's direct sum of two complex, one-dimensional complex representations, which have to be complex conjugate because complex conjugation preserves R2. So it's like C with one action, and then you have C with like zeta, and you have C with zeta bar. This is what happens with rotations after tensor multiplication. So for matrix of rotation is this, right? Good. In complex coordinates. Okay. Yeah, so the important, how you would solve this problem about tetrahedron, you would just say that all representations are direct summands of the group. You have this group algebra. So you know that all irreducible representations are direct summands here. But then, in fact, it's possible to show that every representation V occurs here as many times as its dimension. Then this allows you to just classify all representations, like write a complete list of representations of their tetrahedron isometries, which is just S4. Okay. I'm sorry about this. I was. So the next lecture. Good. So today I will give the last lecture about the affine varieties. People don't like to work with affine varieties for obvious reasons. There are two reasons, in fact. The first reason is that for compact algebraic varieties, which I didn't define, but I will, complex analytic is the same as algebraic. There's no difference. And this is very convenient. Another reason is that you can apply topology. For instance, if you have two curves in a complex variety, like complex projective plane, the number of intersection points can be computed using homology. There's no way to compute the number of intersection points of two curves in C2, for instance. You have two lines in C2. They could be parallel, or they could intersect. There is no difference between these two. I mean, it's very hard to make any difference from this to that. Of course, these two guys intersect at infinity, so for projective point of view, this is the same. Anyway, you study the projective manifolds by going local and study affine. So we finish with this affine and we go to projective. Okay, so this is something which we had already. Every algebraic variety is a ramified cover. Should I give you more explanation about that? So if you have, the first statement that if you have X affine variety, then you have Z, which is birational to X, and Z apply is equipped with a cover, like ramified finite map, and dominant. Right? And well, this is, you don't need birational, but what you also use here, that it is d-sheeted, so it's d ramified cover. And second, that Z is general, well, outside of the discriminant. This is smooth. Because it's ramified cover, then the same is true about X, because Z is different from X only on a divisor. Now clear? Okay. This is one thing. Let's define the tile. This is a very convenient word because it just shortens the local diffeomorphism. So definition, if you have X to Y, you can define that in smooth context, in complex analytic context, in algebraic context. So here I define it for smooth, but it doesn't matter. Differentiable map of smooth varieties is called étale if for each point x in X there exists open neighborhood U containing X such that f from U to its image is diffeomorphism. It's what do you mean by local diffeomorphism? Local in X. You can ask about local in Y, and it would be essentially, well, we ask about local in X. Okay. And this is just a restatement of this claim. So claim, let X be affine, irreducible affine, irreducible affine. Then you have a transcendental degree, transcendence degree of X is, say, is it N here or D? N. You have a map, finite map from X to finite dominant map from X to Cn, which we have constructed, is étale outside Thank you. Is étale outside divisor? Okay, so here I give the proof, but well, I had it, it's here. So we just the same, I mean, this is the same statement as was written there, just slightly restated. So proof first we replace, you have a maps X from Cn, then you have X1 to Cn, and this is, they have same normalization. So this is a birational map, and this X1 is D-sheeted cover. This is just one-to-one diffeomorphism and even algebraic isomorphism outside of a divisor, and this is étale outside of the, so this, say, let's call it F, let's call this G, F diffeomorphism outside of divisor, and G covering outside of discriminant, which is also divisor. So here you have an open embedding if you remove this exceptional set for F, and here you have a decovering. Questions? There's nothing to prove. Okay, transcendental dimension, this is something we already had. I just remind you the, I don't need to write that unless you want me to, because you had it already. So transcendence degree of a variety is the transcendence degree of its field of fractions, and this is the field of rational functions on a variety, and this is just the number of transcendental generators over C. Okay, but now we have a notion of transcendental dimension. So definition, M affine, irreducible. Okay, I'm always assume everything is irreducible here, because if you have non-irreducible variety, it might have several components which have different dimension. And then you need to take some conventions about how you define dimension in case you have different components. Typically, people define it as a maximal dimension of these components, but it's not a common convention. It's not always good. So it's better to assume irreducibility even if you don't need it for most arguments. So M affine irreducible. K of M, it's field of fractions, rational functions of fractions of field of fractions of the regular functions, which is rational functions to M. Then transcendental dimension of M is transcends degree of this field over C. But we know that this is the same as dimension of this same as dimension of same as n in the finite dominant map from M to Cn. And now, by the way, you can see that it is, of course, we didn't prove that transcends dimension is independent from the choice. It was left to you as an exercise. But now it's proven, at least for this situation, because suppose you have two maps from Cn. Suppose you have M map from Cn, which is finite dominant, and map to Cm, which is finite dominant. Then M is locally diffeomorphic to Cn and to Cm. It's not hard to see that there's no diffeomorphism between Cn and Cm for different, n-dimensional and m-dimensional spaces of different dimensions cannot be diffeomorphic. So this is impossible. It's a simple topological fact which you can prove yourself or ask me. It's a good exercise if you learn topology. Okay. Now I have this proposition which explains, by the way, what I just said, proposition, dimension of, I didn't define you the dimension, I'm afraid, so let me define the dimension first. So you have definition, dimension of M is dimension of smooth part of M over, so if the smooth part, if denote the smooth part M smooth, if M smooth is locally diffeomorphic to open subset and open ball B in open B in Cn, a dimension of M is N. Well, to be correct, of course, entirely correct, I have to prove that it is connected. Otherwise, it doesn't make much sense. But you have this result, which shows you that if you have a irreducible algebraic variety, it's outside of a divisor, it's still diffeomorphic, locally diffeomorphic to N. So it has, it's diffeomorphic to N on outside of a closed, in an open dense set. So it can't have two parts, one of this one dimension, the other is different dimension. This cannot happen because of this, because it is a ramified cover. Okay, now proposition. dimension of M is transcendent dimension of M. Okay, how you do that? It's pretty much obvious. You know that transcendent dimension is such n such that there exists this finite-dimensional map. But then this finite-dimensional map is locally a diffeomorphism. This means that M has precisely n dimension if it is transcendent dimension is n. That's all. So there's nothing to prove after we already had this picture. Am I clear? Good. Okay, I'm now going to prove you something which is pretty obvious. Suppose I have a divisor in Cn. Then this divisor has to be n-1 dimensional. To do that, I have to remind you this, what we had already, how we work with smooth things. We use the inverse function theorem and implicit function theorem. Do you have any questions about it? Because I'm going to skip it unless you have any. We had that last time and we have it previously, so it should be known. No question? Good. Okay, now I'm going to prove you. Yes, there's a definition of divisor. We already had it. It's slightly tricky. It's slightly tricky because sometimes you cannot define an irreducible subvariety but by a single equation. So you have an equation which defines a subvariety and it has several components. Each of these components is called divisor. This is not what happens on Cn. As you will see, on Cn, there's as many equations. I mean, a reducible divisor is given by one equation. But for other varieties, it's not true. Okay, even for smooth ones, in fact. It's quite possible to have a variety where every function, where there are divisors which are not given by a single function, even on things like you have elliptic curve, for instance. This is your elliptic curve in R4, but in R2, but you can think of it as elliptic curve on R2. If you have a point, there is not a single function which vanishes at that point because it will vanish somewhere else for most points. Okay, so suppose you have M affine variety. You have principal f of a regular function. It's the zero set of f is divisor. And irreducible components, zero set, let's call it ZF. Irreducible components of ZF are irreducible divisors. Irreducible divisors. And divisor is just union of irreducible divisors. This terminology. The idea is that divisor is something codimension 1. But we didn't define codimension yet, so I had to do this unpleasant definition, and then we shall have that divisor is precisely something of codimension 1. Okay, the good thing that this is not that bad in Cn. So I have this lemma, which is step 1 in the proof of this in the slides. Lemma that I have D in Cn, irreducible divisor. Then D is defined. So this is actually equivalent. D is defined by zeros of polynomial p of z1 dot zn equals 0, where p is irreducible. Okay. Let's prove it. So proof. First, if p is irreducible, then the corresponding ideal is prime. And then the quotient, we take all polynomial functions on Cn, take its quotient by p, is has no z divisors. Then it is irreducible. So then let's call this d. D is irreducible. Clear? Okay, so let's do converse. So suppose you have, so we start with irreducible divisor. Let's start with any divisor. Let's d1 be zeros of polynomial p, polynomial p1. Okay, then you have p1 is a, well, d prime, p prime. P prime is a product of p1, pi, I equal 1 to n, where pi are irreducible. Well, you can also have alpha, it doesn't matter. Then d prime is a union of di, where di are zeros of pi. Right? This is an irreducible decomposition of pi. Then each irreducible component of d is zeros of polynomial. Okay. So for we obtain the following, that in Cn, divisors are precisely zeros of polynomials. Irreducible divisors are zeros of irreducible polynomials. Am I clear? These are questions. It would be nice if you do. Okay, now let's prove this proposition. I'm going to use it, so it's proposition 1. Suppose you have d inside Cn, irreducible divisor. Then dimension of d is n minus 1. Intuitively, this is completely obvious, but our intuition is based on pictures, and we really have to prove it. Even that existence of smooth points, it's not entirely obvious. So this is also not obvious. Okay, so here is a step 1 that step 1, which I just explained to you. D is zeros of irreducible polynomial p. Step 2 is that p prime doesn't belong to the ideal generated by p. It's smaller degree, right? Then by Hilbert Nullstellensatz, p prime doesn't vanish on D. I mean, if it vanishes on D, then it belongs to this ideal, and it doesn't. Right? Okay. And then you have this means that D P. Well, sorry, P prime. I'm slightly. I'm doing something wrong. It's d by dzi of P. Because we can take derivative in any variable, of course, it could be 0. But for some variable, it is non-zero. I mean, it definitely depends on one of the variables, non-trivially. And we take the variable, and I would numerate it as 1. Just I would renumerate it if. OK. Then dp is non-zero. And then d has smooth point. Good. We know already that it has smooth point. That's fine, but still, I would now just compute the dimension of this smooth point. So this is step 3. I would take projection. So it's pi from Cn, from D to Cn minus 1, projection to coordinates z2 zn. So I forget about the first coordinate. I claim that it is I claim that it suffices to prove that d pi from tangent space to D to Cn minus 1 is isomorphism in all points where this, let's denote it by Q. So this is dp by dzi. Points on all points say z small of z is non-zero. Then I apply inverse function theorem and prove that the dimension of this is equal to dimension of this because this is just diffeomorphism. Okay, so let's see what is the kernel of this map, of the map d pi. So the kernel of d pi from tangent space to D to Cn minus 1 is the same as intersection. You take a subspace. Here I have T and the zeros, zeros, zeros intersected with T, dz of D. Right? Because this is just a kernel of, I mean, this is a projection. And this is a kernel of the projection on the ambient space. But then if this is a non-isomorphism, then the kernel intersects with the subspace. But this, yeah, so since d p by dz1 is non-zero, you can plug this. You can take this differential of P and plug. I mean, this is a linear form on this ambient space, and you can pair it with d by d with a vector field d by dz1. This is equal to dp by dz1. This non-zero. Then this is not in the kernel of this. We're done. Okay. Okay. So we obtain that this is non-zero. Then this intersection is equal to 0, and we're done. Okay. So we compute dimension of a divisor. Now the important dimension is Kuhl dimension. It's the most algebraic kind of dimension, which is, for many reasons, better. For instance, I mean, well, transcendental dimension is no good for many. I mean, it's no good, for instance, if you consider a ring which is not over a field. because then you cannot even, you don't have a field. You have to have a field in the base to make sense of it. And the other dimension is purely topological. It doesn't make sense in algebra at all. But crude dimension makes sense very generally, even for non-Noetherian rings, though for non-Noetherian rings it's bad. But still, it's a good thing. So to do that, I have to introduce a convention. So you have as a convention. Suppose you have a sequence like x1 inside x2, inside x3, inside and so on, inside xn. Its length of this chain is n minus 1. It's a number of these signs. Well, this simplifies some definitions. This is standard. Now definition. Suppose you have a ring. Crude dimension of A is the maximal length of a chain of prime ideals. You have P1 inside not equal to P2, inside and not equal to P3, and so on, inside and not equal to Pn. Is the definition clear? So let's do some examples. Do you have anything else on this slide? Not. Yeah. Let's do examples. So example. Suppose you have A is a field. Then it has only one, or Artinian ring. Then it has only one or Artinian ring. Then A has only one prime ideal for a field, or A quotient by nil radical is direct sum of fields, and then it still has it has many ideals, but they're all non-embedded into each other. So all chains of ideals have length 1. Well, 0. This is just one ideal. So then crude dimension, a dimension of A is 0. Clear? Okay. Another example is a principal ideal ring. So principal everybody remembers what is principal ideal ring? So please raise a hand. Good, thank you very much. So principal ideal ring now is, suppose you have a principal ideal ring, then you have, and you have two prime ideals, P1 and sitting in P2, not equal. Then this is generated by, say, A. This is generated by B. And since B, this sits in there, this means that B is AC. This can't be. Because C, I mean, A is not invertible, so C is not invertible, so they don't belong to the ideal B, but their product belongs. So it's not prime. Of course, you have 0, unless A is equal 0. If A is equal 0, it's okay. Am I right? Oh, A, B is AC. Well, if it is 0, then it's not AC. And then you have all chains. Chains have, unless it is a field or Artinian ring, have form A, 0 belongs not equal to P, and then a dimension is Krull dimension. Dimension is equal to 1. For instance, it is true for Z. It is true for a ring of polynomials of one variable because it's principal ideal ring, and for different versions of Z, such as you can localize Z. Okay. Let me now give you a geometric interpretation of Krull dimension, because we know that principal ideals correspond to, well, ideals correspond to subvarieties, right? Principal ideals correspond to irreducible subvarieties. Good. Now we can define Krull dimension of a variety. Dimension of affine variety is a length, maximal length, of a chain. You have a non-empty subvarieties of, because empty corresponds to the ideal, which is just the whole ring of regular functions, and we don't allow, I'm sorry, I didn't write it, but I meant, so it shouldn't be equal to A. I mean, this is our definition of ideals. We don't allow, it's not A is not an ideal. Maximal chain of subvarieties of non-empty, empty, irreducible subvarieties. You have x1, so you have x1 inside not equal to x2, inside not equal to x3, and so on, and you end up with x, which corresponds to, well, if x is irreducible, if it's not irreducible, then it is, well, xn. You end up with x if it is irreducible. Otherwise, you won't end up with one of the components because you need it to be irreducible. Anyway, so this is, again, gives you the same as we had. So, for instance, points is zero-dimensional. And a curve like C is one-dimensional because C, its ring of regular functions is principal ideal ring. So there is certain correspondence, and in fact we shall prove today that dimension is the same as Krull dimension. Of course, for affine varieties, otherwise it's not defined. But generally it's a nice notion which is quite useful, especially if you do homological algebra. It's really necessary to have it if you compute things like, I don't know, Kazul resolutions for models over a ring. Okay, I'm doing more reminders now. So for a while I forget about the Krull and just give you reminder about local rings Nakayama lemma. So definition, a local ring if A has only one maximal ideal. Okay, and there is a way of producing such rings. You take any principal, any prime ideal. Please ask questions. I would really appreciate it if you can. You can do in Portuguese. I'm learning the language, so it's good for me. Please. Okay. So the localization is the procedure when you just invert some, you take some subset, which is multiplicatively closed, and you add fractions. You divide by the elements of this subset, and you can do this with a complement to a prime ideal. Complement to a prime ideal is a nice set which is closed under multiplication, and you can invert everything in it, and you obtain a thing which is local. And this is how one obtains local rings always. You take a prime ideal, you invert, you obtain a maximal ideal. Okay, now I have this Nakayama lemma for local rings. You have A Noetherian and local. Okay, P maximal ideal. Maximal ideal. And M is, well, finally generated A model. Finally generated A model. Then non-zero. So it's non-zero. Then M is not equal to P times M. Okay, and there is even written, I have even wrote a proof here, but if this is actually the best statement of Nakayama lemma, which is most useful, is about local rings. We didn't use it for local rings, but today we will. I did it, actually. It was some time ago. But the proof is very easy. Okay, we have standard Nakayama lemma, which tells us that if Pm is equal to M, then 1 plus P multiplied by M is 0. And then 1 plus P for local ring, it clearly doesn't belong to this maximal ideal, so it's invertible. You have something invertible times M is equal to 0. This means that M is equal to 0. Clear? Okay. So there is, what I'm going to tell you now is called going up and going down, going up and go down. So you can, the idea is that you have finite morphisms from X to Y. Then first you have a subvariety here. This gives you a subvariety there. If you have a subvariety there, it's always obtained as an image of subvariety, but could be many of them. This is the statement about going up and going down. So you have, the same is true for ideals. So I'm stating for ideals. So first let me use this definition. It's not very standard, but I have seen it sometimes. Just to simplify the discussion, suppose I have B containing A rings, and B is finitely generated as A model. Then B is called finite extension of A. Okay, now theorem, well, lemma 1. So you have B containing A, and this is a theorem about going down. So you have B in containing A, finite extension. You don't need Noetherianity here, I think. For the next slide you will. And now you have a non-zero prime ideal Q in B, non-zero prime ideal. then Q intersected with A is non-zero. Again, it's prime ideal, but it's clearly prime because quotient by it has no z divisors, non-zero prime. So the only non-trivial part is that it is non-zero. Okay, so let's prove it. Proof. We take, we localize with respect to all elements in P. So you have so this is called P. I denote it as P. So we take AP is A localized in S, where S is A without P. This is a local ring which, you start with an ideal P. And then you define BP by the same localization. So localized with respect to elements in A. Then BP is finite extension of AP. This is sort of easy because the generators for B give you generators for BP. You just added some more scalars like denominators. It doesn't, stop generators, they remain generators. Okay. Then if P is equal 0, then AP quotient by P, AP is a field because you localized over all non-zero elements in a ring. It has to be a field, right? Then BP is finite torsion-free, finite no-zero divisors. It has no zero divisors because you localize over something which is outside of, it actually belongs, so this actually is a subring in BQ, and this is, right? And this contains B. So B sits here. Okay, B is finite, no zero divisors over AP, which is a field. Then it is a field. This follows from our classification of Artinian rings. It has to be a field extension. Good. But then BP, it's a contradiction. It cannot be because BP contains a Q, which is non-zero ideal. You can localize BP in, you can localize B in Q. This gives you a maximal, this gives you a local ring which has non-trivial ideal. Because as we have discussed, you can actually embed a ring into its localization with respect to an ideal, prime ideal. Okay, am I clear? Let's go with finish with going up, and then we shall have a break. So going up is very similar result. I call it lemma 2. And the notation will be pretty much the same. Again, B and A, finite extension. But now we have everything is Noetherian. Yes, it's written there, of Noetherian rings. it's sort of easy that if A is Noetherian, then B is also Noetherian because it's finitely generated. And yeah. Then for each prime ideal P in A, there exist finitely many, at least one, prime ideal Q in B, such that P is equal to Q intersected with A. Okay, and the proof, step 1, is something which is not related to anything. It's just pure formal statement about local rings and localization. You have AP, as usual, is A of S minus 1, where S is written there. You have a map from A to AP to a P quotient by P. It's kernel of this map. Let's call it psi. Psi is equal to P. This is an embedding. Okay, you can do the opposite way. So you can take A quotient to A by P. This kernel of this is P, and then you take localization, and this is the same map. And this is an embedding because this is prime ideal. Okay, so step 2. Now you have okay, so we have P, we need Q. You have BP. Again is B localized in S in this ideal. And then you can take its quotient by P. So BP quotient by P is finite over AP quotient by P. This is a field. Then you have it's finite. I mean, it's finite generated. Then it is Artinian. And then let's call this R. R quotient by nil radical is direct sum of fields. Very good. And because then it has many prime ideals. So let's take Q tilde is this, let's call this R, this R0 prime. Then you can take intersect the pre-image. You have B into R0, the natural part. It's a projection from B and then localization. And you take Q, let's call it phi. Phi minus 1 of Q bar. Q tilde is Q. This prime ideal, because this is prime ideal. Pre-image of prime ideal is always prime. And then Q intersected with A is precisely kernel of this map psi. Because it's element in A which are mapped to 0 under the projection to P. Then it is equal to P after a projection to this field. Okay, this is time for a break. You have 5 minutes until 14:39. Please. No, it contains P. It belongs to BP, it contains P by construction.
Yeah, I mean, it's not intersect with AP.
Why?
If you say that the
No, it intersects because Q is, I mean, this is what you have. The intersection of Q with A is P. It has to intersect. Because it has to intersect with A because it contains P. By construction, it has to contain P because, yeah, this is Q tilde in R0, and then you take its preimage, Q. But its preimage of 0 is P. So Q contains P by construction. Okay. There's this generalization of this result. It's about chains. So you have a chain of ideals. It's called Cohen-Seidenberg theorem. In fact, it doesn't called Cohen-Seidenberg in much of literature, so it took me some time to, usually it's called going up and going down theorem. But I guess it would be better to credit it to authors. Okay, you have A containing, B containing A, a finite extension. Okay, what else? Noetherian. Did I write Noetherian here? Yes, I didn't forget it. And then you have a chain of prime ideals. Q1 is contained in Q2, contained in Q3, and so on, contained at Qn, chain of in B, prime ideals. And then you have Pi is Q intersected with A, I. Okay, and then first, this is going down theorem. P1 is contained in P2, is contained to P3, and so on. Proper inclusions. They are not equal. And second, for each chain of Pi, there exists a chain. Each chain of Pi is obtained this way. So if you have a chain of ideals in A, it can be lifted to a chain of ideals of B. So who of you already knows this? Okay, thank you very much. So let's prove it. It's not terribly hard now. In fact, it's just applications of these two lemmas. So the first part is for the first lemma, the second for the second lemma. So we need to show that P, say, if Q is properly embedded, Q1 properly embedded to Q2, then P1 is properly embedded to P2. Okay, we can take a quotient by taking quotient by P1 Q1. Can assume that P1 Q1 is equal 0. This gives you non-zero. So you have Q inside A, non-zero prime. And you need to show that inside B, P, which is equal to Q intersected with A is non-zero. This is precisely, this is the lemma 1. Okay? Good. Now, this was going, this part, going down. Let's go up. I can erase lemma 1 now because we won't need it. And the proof is still the same. But now you use induction because you need we need to lift ideals according, inductively so that they are contained in each other. So step 2, proof of the second statement. Suppose induction. Suppose we lifted P1 up to Pr. So you have Q1 contained in Q2 and so on up to Qr. And then Qi intersected with A is Pi. And we need to find Qr plus 1. First, we can take quotient. So we replace, because the prime ideals contained in Qr are the same as prime ideals in the quotient by Qr. So that we can replace B by B quotient to Qr, A by A quotient by Pr. And we need to find Pr plus 1. Let's hold tilde. This is prime ideal, non-zero prime ideal, non-zero prime ideal in A quotient by Pr. This is the image of our Pr plus 1, which is contained in B quotient by Qr, and this is finite. To see that it is finite, you just realize that, just the same generators, here and there. Good. It can be lifted. So lemma 2, P tilde R plus 1 is intersection of Q tilde R plus 1 intersected with A quotient by PR. Right? You just apply, you have an ideal, you have two rings, you have an ideal there, you lift it to an ideal there, which is prime. Then preimage of QR plus 1 tilde in B is QR, which has the same property, plus 1, that after intersection with A, it gives P tilde PPR plus 1. Good. Questions? Okay, so now this is these two guys. They both are students of Zariski in Johns Hopkins University, same year, but they published this paper slightly later after, but more or less just as they graduated. And then Seidenberg was lived quite a happy life, and Cohen unfortunately committed suicide in his 30s because he was very critical of himself as a mathematician, and then he decided that he's a failure. He would never do anything as good as his thesis, and it was his downfall. But I couldn't even find his picture. It's doesn't exist on the internet. I tried, but at least this is his tombstone. Okay. So Krull already had this argument, but it was very unclean. I forgot to put the picture of Krull, but so his ideas were there, except that it was not that general and not that nice statement that he had. Okay, now I will use this go up and go down to prove that first I will prove invariance of Krull dimension. It's almost clear. So theorem, lemma, or corollary. Suppose you have x to y, finite map. And then Krull dimension of x is equal to Krull dimension okay, why it is so? Well, the Krull dimension, there's nothing to prove essentially. The Krull dimension is the maximal length of chain of prime ideals, like that. But then for each chain downstairs, you have a chain upstairs, and vice versa. So each chain in OX gives you a chain in OY, and chain in OY gives you a chain of OX at the same length. So there's a equivalence of the length of maximal length of the possible chains. And it's important that they remain distinct. This is the first statement of Cohen-Zeidenberg, and the second is that you can always lift. Obviously, if you lift, it remains distinct because there are distinct downstairs, and the downstairs they are obtained by intersection of Q with A, so they remain distinct upstairs. The going down and going up gives you a distinct chain from distinct chain and vice versa. Okay, and now we have, finally, we can prove this main theorem about a dimension, Krull dimension, just n dimension. They're equal. So theorem, Krull, let's denote Krull dimension dim Krull dimension for each affine variety x, dim x is equal to dim Krull of x. Okay, so the first observation is that both notions are invariant under projection. We proved that. So prove. Step one. Dim k and dim are invariant under finite dominant maps. Finite dominant maps. Well, we prove it. I stated it only for our particular finite dominant map to Cn, but we shall only use it for the map to Cn. And still, the same argument actually works here for general finite projections. So you have x, at least a map from x to Cn. So the Krull dimension of x is equal to Krull dimension of Cn because it's finite. And yeah, it should be dominant. Because we assume that B is contained in A is contained in B. So this is OY is A, OX is B, and they're contained. So you have to assume dominant here. I think it's, yeah, finite dominant morphism. Because, I mean, a map from a point to Cn is also finite, and it's clearly bad. So for finite dominant, it works. Good. Then need to show it only for Cn. Okay. So we're almost done because Now we will just use induction. Step 2. So, well, suppose you have D inside Cn, a divisor, irreducible divisor. Then D, the ideal of D is generated by, its principle is generated by a irreducible polynomial. Irreducible polynomial. Therefore, there's no intermediate ideals. Ideals between 0, like contained not equal to something, contained in P. Because no. Sorry. It's vice versa. It's written here wrongly. There's, of course, I'm sorry. There's no intermediate ideal because between this and or D or Cn. Because if this is contained in, I'm sorry. Could you correct me, anyone? So what is? Now I'm very bad with inclusion of ideals. So if you have P contained in something, okay. So this this ideal. Oh no, it was correct to begin with. So you have P, something here. It's contained into P. Right. Sorry. Doesn't exist because this would be this would be also this would be an ideal which is generated by some element like PQ and maybe something else. But what is important is that both P and Q doesn't belong to here. Then this can't be prime. Am I clear? Okay. Sorry. Now we have, so this is impossible because this is irreducible polynomial. And this is principal ideal. On the other hand, for any chain, you have 0 is contained into some, so any chain starts with 0 because 0 is irreducible. You can always add 0. It contains something. Then it contains another ideal, say I. Then, so if it is the second step, so 0 is contained in I, there is no, we can, every prime ideal contains, if a prime ideal contains a polynomial P, then P, let's take irreducible decomposition for P. One of the components of that irreducible decomposition is also contained in I, because their product is contained in I. So you have this Pi reducible, and you have P, this irreducible, this prime ideal here. For each ideal, you have a prime ideal there. Then this, since it's a minimal chain, this means that they're actually equal. So you start, the first step of any maximal chain of prime ideals is principal ideal of this form. Okay, let me write it. So, for each chain of prime ideals. 0 not equal to I1, not equal to I2, not equal and so on inside OCN. I1 is P over P irreducible. Okay, this means that dimension of OCN quotient by P, the Krull dimension, is the same as dimension of CN minus 1. Because any chain in this quotient is just less in length than by 1. Good. Now we can finish by using induction. Step 3. Suppose that dimension k of x of y is equal to dimension of y for each y with dimension of y less than dimension of x. Then dimension k of divisor d is equal to dimension of divisor d. This we know. This is dimension n minus 1. This is what we proved. It's proposition 1 in this lecture. And this we also know. It's dimension of Cn minus 1. Okay, minus 1, but then dimension of Cn is equal n. Just adding n to this, 1 to these two parts. Okay, I think I'm on time. 3 minutes late, sorry. But if you have any questions, please ask. Otherwise, so this was the last lecture on affine varieties. So next we shall do with complex projective space. So how many of you already know what is complex projective space, by the way? Good. And what are affine coordinates? Good. Thank you very much.